I will sit, I think.
Okay.
I'm sorry, I have a sciatic pain, and I I prefer to sit while I'm speaking. So sorry for that. Oh, huh? We have to put on the.
All right.
Okay, all set. First, what? Maíz Mabaya? Huh? Okay. First, I would like to thank Shabtai Cohen and Uri Hofgeber for organizing and initiating the symposium. Both of them carry to new frontiers subjects that have preoccupied me during my career. If I have accomplished anything, I owe it to the students who chose me for their guidance. Their achievements is probably the subject that gives me most of the pride. I also must thank the harmonious collaboration of excellent, marvelous colleagues. There is also something I have to be thankful for, is the spirit of this institute, which supports and encourages creative thinking. I hope that this spirit is still reigning and will continue to be the, the, the trademark of this institute. As you have heard from Pedro, and I think also from John Orman, one of the traits of my character is to take a reverse view of accepted concepts. Think differently. The role of capacitance as a subject came up when Uri Hochberg, during a coffee break after a lecture on transpiration, asked me why foliage vapor conductance and vapor flux density shared the same dimensions and were expressed with the same units. Uri's expertise is plant hydraulics, the flow of water of sap in plants. Both transpiration and sap flow are transport of water molecules pushed by pressure gradients. They are physically analogous, and therefore it is natural that they should have the same expression and the same physical dimension. The question intrigued me, and so I checked the literature, and I found that the units assigned to plant hydraulic conductance and those assigned to foliage vapor conductance differ. A flagrant illustration of this is in a study that relates plant hydraulic conductance to stomatal conductance. On the same figure, hydraulic conductance and foliage conductance of vapor are expressed with different units, as you can see here. In order to answer this possible enigma that this difference suggests, I am looking at the expression of transport of vapor. Transpiration is proportional to the vapor pressure difference between inside the leaves and the ambient air. G sub V is the conductance and expresses the ability of water molecules to pass through stomata, the viscous layer that surrounds the leaves, and the ambient convective space. But in the equation, we have also the barometric pressure appearing. What is its role? To find out that, I address the ideal gas law and apply it to air and to vapor. And we find that omega sub V, the vapor mole fraction, which is dimensionless, is equal to the ratio between vapor pressure and barometric pressure. Taking its derivative expresses the amount of water vapor that has to be changed in order to change the vapor pressure by 1 Pascal. This property is what we call capacitance. I qualify it as pneumatic because it relates to air. And when you calculate this derivative, you find it is equal to a reciprocal of barometric pressure. This defines the role of the barometric pressure in the equation. We can now simplify it by writing it as the product of kappa V, a coefficient, and the vapor pressure difference. And kappa V is equal to the product of the capacitance by the conductance. This is a result I will ask you to remember because I will address it later on in my talk. For sap flow, the situation is more complex because the water potential at root entry is not accessible to measurement. It is buried into the soil, and we cannot go to there. An experiment in a mature citrus tree circumvents this difficulty. Measuring the sap flow and the leaf water potential at hourly intervals during one day after an irrigation displays a linear relationship. At the intercept of the y-axis, the root water potential and the leaf water potential must be equal, and therefore we find a way of determining its value. The coefficient kappa sub x is the reciprocal of the slope of this line. Irrigation was then interrupted and measurements were continued 1 week later. Reproducing the same results as the initial measurements. It was then continued for the next 6 weeks, showing the same pattern and the same type of relationship with a decrease, a progressive decrease of the leaf water potential and a decrease of the sap flow. After 6 weeks, the trees started to lose their leaves, and so irrigation was restored, and the square symbols indicate the measurements taken 1 day after renewal of the irrigation. It returns to the very closely to the original data, indicating that the drought did not impair irreversibly the transport properties of the tree. But during the course of the experiment, the coefficient kappa sub x decreased moderately. If kappa sub x is the hydraulic conductance, it is the expression of the friction of water molecules on the walls of the conducting vessels. But also it expresses the cohesion of the water column. As during the experiment, the water potential decreased considerably, we know that the decrease of water potential causes cavitation that breaks the cohesion of the water columns. In some of the vessels, inducing by this a decrease of the drop of the hydraulic conductance. We did not measure cavitation in this experiment, so I refer to some measurements taken by Terry and Young, which show that at water potentials below minus 2.5 megapascals, the intensity of cavitation increases by a factor of 4, and below minus 3 Pascal by an order of magnitude. During the experiment, during the last 3 weeks of the experiment, the water potential was way below minus 2.5 megapascals. Still, despite this identification of the cavitation, the decrease of the coefficient kappa was minor. This, of course, is incompatible with logic. We should expect a much sharper decrease in conductance, which is not shown by the coefficient kappa. So kappa sub x doesn't seem to be really the conductance, because it does not behave like a conductance should. In order to address the dimensional issue first, we compare the formulation of sap flow with vapor flow. Remembering what I said previously, that I was going to indicate what was the significance of kappa sub v, and now by analogy with these findings, we address what is the significance of kappa sub x, the coefficient that originally was thought to be the conductance, the hydraulic conductance, but probably is something different. The analogy sets it as the product of two entities, the hydraulic capacitance and the true value of the hydraulic conductance. When we look now at the units which express the dimensions of these two quantities, we see that they are equivalent. So this so that invoking hydraulic capacitance resolves the dimension enigma that we started with. For the experimental issue, we need to determine the value of the hydraulic capacitance. This can be found by considering the water retention function of the citrus leaf. We see that when the leaf water potential decreases, the value of this capacitance, which is the reverse of the slope, is the reciprocal of the slope of the lines, increases by a factor of 5 when the leaf water potential decreases below minus 2 megapascals. When we compare this with the occurrence of cavitation, we see that there is a correspondence, there is a parallel between the change in the hydraulic capacitance and the intensity of the cavitation. We use now this finding to calculate the value of the true value of the conductance and show that, that on the 3 last days of the experiment, the hydraulic conductance, the true value of the conductance of the hydraulic conductance decreases tremendously, so that it resolves also the issue raised by the occurrence of cavitation and its effect on hydraulic conductance. We still need to try to understand the significance of this result. And this is obtained when we compare the water retention function in an inert medium like clay with a retention function, water retention function of a living leaf. In the soil, the hydraulic capacitance is the maximum at the high range of the water potential. And it decreases as the water potential of the soil drops. By contrast, in the leaf, it is lowest at the low capacity, at the low water, at the lower water potential, and maximum and increases as the leaf water potential drops. This characteristic of the water, the relationship between water potential and water content in leaves is the result of a biological process, because most of the water in leaves is contained in living cells enclosed by semi-permeable membranes and determined by metabolism that regulates the osmolarity that controls the entry and exit of water from cells. Therefore, plant hydraulic capacitance assigns the biological characteristic of associated with sap absence. By contrast, hydraulic conductance is purely physical, expressing the friction and column cohesion. I cannot close my my lecture without stressing the importance of the Tyree and Young paper that really provides the key to the technical tree and the experimental way of defining this characteristic. If you want to find more details, and a more systematic explanation of what I've just said, this is a paper that describes it. I cannot also finish by reminding you that what initiated this project is the casual conversation with Uri Hochberg, and stresses the importance of coffee breaks for science. It also sets the significance of my farewell message. Thank you. Well, okay, I think I understood the question. The question is, how come, why does uh, the uh, uh, the hydraulic capacitance help the uptake of water and the flow of sap? Because you have to consider two properties in order to explain flow. One property, which is the generally accepted property, is conductance. But capacitance has also an important role because, in fact, capacitance expresses the the ease, the amount of energy that has to be uh, uh, produced in order uh, uh, to move molecules. Okay, and so and this is the reason why uh, the change in hydraulic conductance is not the only factor that determines the relationship between flow and uh, water potential gradient. Yes, I'm not sure I understand that.
You're talking about whether there's cavitation recovery. Yes. So we assume there's no cavitation recovery.
Well, the recovery is exactly what I told you. It's the effect of the capacitance. The capacitance is
So you're saying that
because
there may be not cavitation in the vessels, but there's some other capacitance. If we assume that there's no
no.
cavitation,
What is let me. I think I understand. What is cavitation? What is cavitation? Cavitation is the breakage of the water column. It is not embolism. Embolism is something completely different. Cavitation is the breakage of the column. And why does the column break? Because uh, the sap contains not only water and some solutes, it also contains dissolved gas, air, CO2, and some other. When the water potential drops, the solubility of these gases decreases, and this is what causes the cavitation. The cavitation is caused by the uh, by the release of air that is of gases that are dissolved in the water. When the potential finally drops down, the solubility of these gases increases again, and this causes the closure of the water column and its restitution. If there is embolism, embolism is the entry of, of a gas through a breakage in the conducting vessel. And if there is a breakage of, and this is irreversible, this is an irreversible damage. So this is why we have this process. Okay? That's right.
that's what the data says. Okay. Thank you very much.